Hello students, in this video we'll discuss how you compute the probability of a union of two events. So we'll discuss the probability of the union of two events. So what we'll do is we'll let A and B be subsets of the sample space. And we want the Venn diagram for this configuration. Now, a couple things are possible. So here's our sample space, S. So my set A might be something like this. And now B can be any other subset of S. So there's no restrictions on what B can look like. So maybe B looks something like this. That's my set B. Now, there are points in my sample space which are both in A and B. So this little area in between there is going to be the set A and B. This part of the set over here, that's not in the pink region, so this set over here, that blue set, is going to be B and not A, or A complement, or we can use the bar notation, B and A bar. And then this set over here is the set A and not B. And so our question now becomes, how to compute the probability of A or B. And we recall from the axioms of probability, here's a fact. If A intersect B is empty, that means they're mutually exclusive or disjoint. So if I have disjoint events or mutually exclusive, then the probability of A union B, by the definitions of probability, is the probability of A plus the probability of B. But it's not necessarily true that and this is the case. But what we can do now is we can say, okay, well, these sets, note, A intersect B complement, A intersect B, and B intersect A complement, the three parts over here, this part, and this part, are mutually exclusive, or disjoint from each other. So, and their union is A union B. And A union B is A intersect B complement plus A intersect B, union A intersect B, union B intersect A complement. And so what we can do now is we can write the probability of A as the probability of A and B complement plus the probability of A and B. And likewise, I can write the probability of B as the probability of B intersect A complement plus the probability of A intersect B. And so now from these relationships, what we can deduce is the following. We have now that the probability of A union B is the probability of A intersect B complement plus the probability of A intersect B plus the probability of B intersect A complement. And we have formulas for all of these things. So we know, for example, that if I want to compute the probability of A intersect B complement, A intersect B complement is exactly the probability of A minus the probability of A union B. So this is the probability of A minus the probability of A union B. Then I have to add in this probability over here. That goes right down. Probability of A intersect B. And if I want to find the probability of B intersect A, the probability of B intersect A is the probability of B minus the probability of A intersect B. So this thing over here is the probability of B minus the probability of A intersect B. And now I have two negatives of these things and one positive, so those will cancel. And I'm left with the formula that this is equal to the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. So, and that makes sense too, because if I compute the probability of A, I'll get one copy of this pink intersection. If I compute the probability of B, I'll get another copy of that pink intersection. But I've double counted that pink intersection in terms of probabilities, so I have to subtract off one copy of it. It's an example of double counting. So if I was to neglect this, subtracting A intersect B, I will have counted that middle region, that pink region, twice when computing the probability. So the probability of A union B is the probability of A. So we can write it over here. The probability of A union B is the probability of A plus the probability of B minus the double count, A intersect B. And this relationship is very useful for computing probabilities. Thank you very much.